In this video, we are going to explain about the concept behind the derivation of diffusivity equation.
Before that, we will kick off with a linear reservoir system of one directional flow in the x-axis. The control volume of this system is highlighted in blue color. The whole system is having a uniform thickness. By applying the principle of conservation of mass, the mass of fluid flowing in minus the mass of fluid flowing out is equal to the mass of fluid accumulated in the control volume. Now let us define the formula of mass by knowing the mass flow rate is equal to volumetric flow rate multiplied with density, and we know that Q is equal to area times velocity. So we can substitute Q and move T from left to right. Here we got the formula for mass. Here we are trying to derive the mass of fluid flowing in. We add the position which x plus delta x to the mass formula. Obviously area is width times height. Easily we substitute, rearrange, and that's it. For mass flowing out, we apply the same theory by adding the position which is x. Area is still width times height, and there we go. Mass accumulation is basically the difference in volume multiplied with total fluid density. The reason why porosity is involved is simply because we are going to know the fluid density alone, where total density multiplies porosity equals to fluid density. Bam! Volume is substituted with width times height times length. The final equation is then put together to form mass conservation formula. We will then divide the whole equation by width, height, difference in time, and length. Are you bored? If yes, then you're about to sleep in a while. But sleep is only for losers. The equation then we have gotten will then be further simplified by limiting the equation twice, where delta x approaching 0 and delta t approaching 0. Here you have the equation for continuity equation. This lorry here will now bring us to transport equation, where it is driven by a man commonly known as Darcy. Darcy law is famous among us. Reason why 5.615 is multiplied is because we want to convert it to unit barrel per day. Q is equals to V times A. So when you rearrange, it becomes V equals to Q over A. By moving A to left and substitute it with V, we have transport equation. Transport equation is substituted in our continuity equation. The right side of this equation is differentiated using product rule. How to use product rule? There are two unknowns, so we keep one, differentiate the other, plus keep the other one and differentiate the other. Chain rule is applied on delta phi over delta t. The solution then is substituted in. Wait, did we forget compressibility of rock and fluid? Rock compressibility involves with porosity, thus the formula of rock compressibility is substituted in the equation. Let's assume that we have slightly compressible fluid, which directly links to homogeneous reservoir with constant permeability and fluid viscosity. That means we don't have to differentiate them and we bring them out. Using the product rule, we differentiate the rest, and this is the outcome. Substitute it into the original equation. Moving on, we differentiate density in terms of x and t using chain rule, and then fit it back into the equation. Now density is too mainstream, so we cancel them out by dividing itself. This is where fluid compressibility comes in action. This is the formula of C, fluid compressibility. Fluid compressibility is then substituted twice in the equation. We neglect the whole term as it is very small. The equation is further simplified, and as you can see, there's rock compressibility and fluid compressibility on the right side of the equation that leads to total compressibility CT. Equation is rearranged, and finally we've got the diffusivity equation, one in terms of days and the other in hours. Radial flow, ridiculously more complicating part of this topic and your life. Well, this took me hours to draw. Does it look scary? No, it doesn't. It looks like a piece of cake to me. The difference between radial and linear is simple. Linear we use the term x for distance, but in radial we use r, which represents radius. Again, we are finding the equation of mass conservation, but this time in radial flow. So this is the formula for mass in, where flow rate is substituted with area times velocity, and area is further expanded using the area formula of radial flow. Steps are repeated for mass out too. The volume of control volume is differentiated in terms of radius, and then delta R is moved to the right and substituted in the mass accumulation formula. The final equation of mass conservation is derived as following: mass in minus mass out is equals to mass accumulation. The whole equation will be divided by 2 pi r h dr. Now it looks shorter but still complicating. To further simplify this equation, we take delta r and delta t as our limit, and yes, we've got a shorter and simpler equation which we call it as continuity equation. Famous guy who drove us earlier has came back to life. Moving area to the left and substituting it with V gives you transport equation. This equation is substituted in our continuity equation. The equation on the right is differentiated using the product rule. I've explained clearly on how to perform product rule, and if you're still having problem, call me maybe. Taking rock compressibility into account, the formula of Cf is substituted in the equation when the chain rule is applied on delta phi over delta t. Can you realize that the steps are the same as linear flow? We assume that we have homogeneous reservoir as I mentioned earlier. We will have a constant viscosity and constant permeability, so throw away both unknowns which are constant out and differentiate what's in using product rule. Next, we differentiate density in terms of radius and time by using chain rule. Let's simplify the equation by cancelling out the density and then substitute compressibility of fluid C into the equation. Since C on the left side is small, we will have to neglect the whole term, and again on the right side it leads to total compressibility. Now we can rearrange the equation, and that's really a piece of cake. We've got diffusivity equation in terms of day and hours.